Hello, you absolute legends. Osmotic pressure is another collagetive property where the properties of a solution change based on the amount of the solute, not of the identity of the solute. This is a fascinating example. I think it's fascinating, I hope you do too, of trying to determine the molecular weight of a compound that's dissolved in a solution. So, titin is a protein found in skeletal muscle. It effectively can be described as an anchor that connects some of the tensile portions to the sidewalls of the muscle belly. And it's a huge protein. So I have squiggles here trying to show that protein or imagine that protein structure of like the alpha, beta helixes, and quaternary structure. Keep in mind that sometimes this squiggle here is meant to represent hundreds of thousands of atoms, okay? Sometimes I draw circles and it represents just one atom or 30 atoms. This is meant to represent, think of like all the stars in the sky. Like that's how many atoms I'm trying to draw here. You would make a in a laboratory situation, this solution would be some sort of buffer with stabilizer that can keep the titin protein units individualized and not coagulate or decompose, so that way you can get good consistent readings on your instrument. Your instrument would effectively try to measure the pressure that's in the headspace of this right here to get the osmotic pressure. Now, solutions and gases behave similarly. That's why we can take headspace pressure measurements to determine what's going on with the pressure here. Because of their similar behavior, solutions and gases, and the atomic vision, the behavior that's impossible to draw on here completely, the chaotic movements, the tumbling, that behavior, we can use the gas law constant, the R, as trying to calculate part of the solution here. So R let me write that larger. Excuse me, grams per mole of titin. This is what we're trying to solve for. We want our final units in grams per mole. Grams is something I can weigh out in a lab. Yes. And we put in 20 some grams of titin in here. We made this solution, so I know that number. Moles, heck, nice, it's in there. So when I'm setting up my scaffold, I'm absolutely going to have moles in the denominator and grams up top. So this solution that was made, and this would be told to you in the question, what is it, 21.066 grams of titin was used to make this solution, and this total volume is 100 milliliters, or 0.1 liters. So and we know these numbers because they were given to us in the question, or we made them in the laboratory. This gas constant we look up in a textbook or is given to you in the question. The pressure of this solution would be measured by the apparatus, and that is observed. It's an ugly number. It's an ugly number, 1.32 times 10 to the negative third. I'm immediately going to put that into standard notation. let's start setting up our scaffold and start canceling out units. We want grams on top and moles on the bottom. So I'm going to start with that right there because that is grams of Titan. I need moles on the bottom. So because this is up here and this is down here, because that is what I'm looking for, that's what's guiding me. That's what's guiding me. I'm not thinking about it's going to multiply, it's going to divide. I'm not thinking about a formula. I'm just trying to make these units build up to look like that. Now I got to start canceling all this other crap that I don't want anymore. Liters. Top cancels out bottom. ATM pressure. That cancels out. The only unit left is Kelvin right here. This was done at 25 degrees centigrade. That's given to you in the problem. So 298 Kelvin, converting centigrade, Celsius to Kelvin. Got to do that. I didn't do that on here. But I made all my units cancel. So that way the only things left are grams divided by moles. I'll tell you right now, this is a huge number. I hope this helps. Thank you.